Objective 1, an introduction to imaginary numbers and solutions. So moving forward as you solve quadratic functions, up until now we've been solving via factoring. And with factoring, when you can solve with a factoring strategy that we've worked with, either finding the greatest common factor, MACAB T-chart, or difference of squares, all of our solutions have been real numbers. Now, moving forward, we're going to start working with quadratic functions that will have solutions that are not real numbers. And so we're going to start talking about what's called an imaginary number. So, in this objective again, by the end of this video, hopefully you have a better understanding of the imaginary unit I and when it shows itself and why it was needed, or why it needed to be created by mathematicians long, long ago. So to begin, sometimes we will encounter equations that have no real solutions. So we have to rely on a number system with the imaginary unit indicated by the letter I. To discuss why this exists, let's first look at the positive version of a perfect square. So we can take the square root of positive numbers like the square root of 9, and that equals 3. Because 3 squared goes back to 9. Technically, the correct answer is plus or minus 3. Because if you consider this, the positive version of 3, 3 squared, which technically means 3 times 3 equals 9. And also the negative version of 3 squared. If you look at this, negative 3 times negative 3 also equals positive 9. Because remember, if you multiply two negatives together, they cancel each other out and you get a positive answer. So in this situation, you take the square root of a positive number, you will have two answers always, the plus and minus version of that number. But when we try to take the square root of a negative number, something like the square root of negative 9, we can't do it because no number multiplied by itself will give you a negative. Because again, what we just said and what I wrote in blue right above, it either has to be 3 times 3 equals 9 or negative 3 times negative 3, which gives me back to 9. No combination of numbers would get me back to negative 9. This is why the imaginary number needed to be created. Look more into detail as to why it needed to be created. First, there are two rules that go with it. I equals the square root of negative 1. So now we can take a square root of a negative. And when you take the square root of a negative, instead of writing negative in your answer, you need to replace it with I, and it becomes free of the radical. We'll talk more about that in just a second. The other rule is that I squared equals negative 1. So I talked about this in other videos as well, but the radical sign here and the power of 2 are inverses of each other, meaning they do the opposite thing to numbers. So the square root of negative 1 equals I, and means I squared, which is I times I, equals negative 1. That is very important because now we have a situation where a number, even though it's an imaginary number, times itself can go back to the negative version of the original number. So now we can take the square root and have a situation where you can multiply a number with itself to get back to the negative. Whereas before, up here, the square root of a negative 9 didn't work necessarily because both situations, the positive version of 3 and the negative version of 3, still gave me a positive 9. Now I can get back to a negative number. So let's look at a couple examples. And then we're going to talk about the solutions, real versus imaginary, in this video as well. So example 1, the square root of negative 121. I can consider it just like the square root of positive 121. And if I know my perfect squares, I know that the square root of 121 is 11. And if I remember, both the positive and negative version work to go back to 121. Positive 11 squared is 121, and negative 11 squared is 121, just like I showed you up here in blue. Now, let's consider this though. Taking the square root of a negative means that I need to represent that we're entering into the realm of imaginary numbers. And just like I showed you up here, I'm going to erase this so we can see it a little better. Just like I showed you up here, whenever you take the square root of a negative number, it comes out of your answer, of the radical, it comes out of the radical and is replaced by the letter I. So in this case, the square root of negative 121 is plus or minus 11i. I need to put that I there every time I take the square root of a negative to show that we're entering into the realm of imaginary numbers. So please get that in your head. When you take the square root of a negative, you need an I in your answers. So I'm done with that one. I have solved it, plus or minus 11i. Now, moving on to the next example, the square root of negative 28. Now, the square root of positive 28 is not a perfect square. It comes out to a decimal. So I need to break this down into simple radical terms. So I can use a factor tree. And I can talk about this more specifically in another video, this skill set itself. So just please take notes and consider this skill, but you're going to practice this in further detail in just a little bit. But in order to break this down into simple radical terms, just keep in mind that this negative will reappear as an I later in your answers. And then I just need to factor 28. So I do 7 and 4. 7 times 4 is 28, or 28 divided by 7 is 4. 7 is a prime number, so it cannot be factored anymore. So I can break down 4 still into 2 and 2. When I'm doing this process, I do what's called the prime factorization, meaning I break down the number 28 into factors that can no longer be factored, or prime numbers. Break them down into prime numbers. At this step, I look for pairs. I see a pair of 2s. The way I've explained it in the past is consider this radical to be a house or a jail or somewhere that you're stuck inside of. The only way you can get out of the house or out of the jail is if you have a pair or someone to help you out, someone of the same likeness. And so in this case, the 2s come in pairs, and so they can escape the house. They escape with just the number 2, just one of the 2s. And then stuck inside is the number that didn't have a pair, the 7. So the 7 is still left in the house. And again, the 4 existed here, but that 4 broke down to these two 2s, which came out as this 2 here. To finalize my answer, I need to let everyone know that we're entering into the realm of imaginary numbers because we're taking the square root of a negative. So I need to put an I outside of the radical. And this is the correct form to use. And so please put the number first, then the letter I, then if there is a radical left over, whatever's left inside the radical. Again, I use that I because it tells me that we're entering into the realm of imaginary numbers. And then finally, just like working with the square root of positive numbers, negative numbers still have a plus and a minus version that exist. So my final answer is the plus and minus 2i times the radical of 7. Let's quickly look at why that situation occurs. I'm going to go back to this easier version of 11i. If I do 11i times 11i to try to get back to negative 121, I can do 11 times 11, which is 121, and then I times I is I squared. And one of the rules that exists for the imaginary numbers is that I squared equals negative 1. So this becomes negative 1. So then I get 121 times negative 1. And then finally, 121 times negative 1 is indeed negative 121. And that works with the positive and negative version of 11i. So that's why the I had to be created, because now it creates a pathway to when you work backwards and actually multiply these numbers back together, you can get back to the original negative number that you're taking a square root of. That's why the I had to be created, because it actually finally makes the math work out, or it creates a pathway back to the beginning. And it would work just with this number too. This number is just a little bit more complex, or just not as pretty as the whole number of 11. But it would work, the math would still work if I multiplied it back out. Now, let's go down to considering the real solutions versus imaginary solutions in reference to their graphs.